our n, because n is the normal vector of the surface, therefore n must be orthogonal to this n must be orthogonal to this tangent vector of a curve on the surface. Okay, so this means the inner product is 0. So inner product is 0. We obtain 0 equals gamma 0 and n. The n is unknown. We want to find a formula to compute the n. And this is the inner product of two column vector is the first vector take transport. So this is phi h transport and then multiply by n. Okay, and this is by the computation of metric operation, we see that this is h transport and phi point a transport and then n. This can also be written by h, the inner product of h and phi point a transport and multiply by n. Okay, so we have this computation. I remind you that this is an inner product in Rn because gamma dot 0 and n are all vectors in n-dimensional space. Well, here this inner product is in Rn-1 because H is an n-1 dimensional vector, and as you can see, this is also a vector in Rn-1. Therefore, the inner product here is in n-1 dimensional space. So this result implies what? Because our H is arbitrary. Okay, remember our H is taken arbitrarily here. For any H, this computation is valid. Therefore, H is arbitrary. So this can only happen if this implies that the vector taking inner product with H must be 0. Okay, by the arbitrarily of H, we see that phi point a transport then n should be 0. Because H is arbitrary, we must have this to be 0. So this is the equation to solve for our normal vector n. Okay, how to solve this equation? This equation, I write it next page. The equation is phi point a transport n is 0. This is n-1 by metric and n-dimensional column vector. Okay, so this equation, because the rank of the coefficient matrix, the rank is exactly because transport does not change the rank of a matrix. So this is n-1. So we have n unknown. Our capital N should have n coordinate. We need to determine this n coordinate. So this we have n unknown and we have n-1 equations, and also the rank of the coefficient matrix is n-1. We see that solution of this equation, solution of the equation forms one-dimensional subspace of Rn. Okay, we have an unknown variable and the metric has rank n-1. If the metric has rank R, the solution form an n-R dimensional subspace, linear subspace, a vector subspace of the solution space. You have studied linear algebra, you know this. Okay, but now the rank is n-1, so the solution space is one-dimensional. Geometrically, this means that any multiplication of n, if you have a normal vector, any multiplication of the n are also a normal vector. And these are all the normal vector. Okay, geometrically this is consistent with our algebraic consideration that the normal vector form a one-dimensional subspace. Okay, one-dimensional subspace. So our mission is to find a base vector of this subspace. How to find the base vector? To write the base vector, we need to using the coordinates. Okay, so because the rank of this matrix is n-1, this matrix, the rank is n-1. What's the metric? This metric is x1 1, x1 n-1, xn1, xn n-1. This is the derivative matrix of phi. Okay, here to save space, we use the notation xij is the partial derivative of the xi with respect to j. The phi x is phi u. So x1, xn are the component of x, and u1, un-1 are component of phi. Okay, so the matrix is this matrix. So because the rank is n-1, we might assume that there is an n-1 ordered of determinant which is not zero. So since the rank is n-1, we without loss of generality, we can assume x1, xn-1, the Jacobian determinant of this x1, xn-1 with respect to order u. That is the first n-1 rows of this matrix. We assume that because of the x1 n-1, xn-1 n-1, we assume that this block is no singular. This block is no singular. Okay, the determinant of this block is the Jacobian determinant of x1, xn-1 with respect to order u. So we assume this is not zero. Without loss of generality, we might assume that this is not zero. Of course, we can multiply by a -1 n plus 1. Okay, and we denote this by nm. Okay, we can assume that this Jacobian determinant multiplied by the -1 to the power of n plus 1 is not zero, and we set this to be the nm. Okay, of course, if this is zero, you can consider other n-1 dimensional determinant. Maybe the last n-1 rows of the matrix. Okay, so we only consider this. So this is our nm. Okay, then this equation, the equation can be written in other way. Our equation is phi prime a transport n is 0. This equation can be written as here. This is x11 x1 n minus 1 and xn1 xn n minus 1, the transport, this is the transport of phi prime a, and n is n1, n this is 0. Okay, in coordinate, this equation, this metric equation becomes this system of linear equation, and this equation you can write in a more useful form. That is x11 n1 plus x n minus 1 n minus 1. That is, we use the first rows to multiply this vector. But we move the last term to the right hand side of the equation. The right hand side is 0, but we move the last term of the left hand side to the right hand side. We obtain the d1 x no, not d1. That is x1n and nn. Okay, so the first equation is this. Similarly, we have the other equations. The last equation is n minus 1 n1 plus x n minus 1 n minus 1 n minus 1 is minus x n minus 1 n capital N. Okay, this is the result of the last row of the matrix. Multiply the vector n1 nm, and then move the last term on the left hand side to the right hand side. Okay, so we get this equation. The determinant of this of the coefficient matrix of this equation is not 0. The determinant is precisely x1 xn minus 1 over u1 un minus 1. All the derivative, all the partial derivative are taken at the point A. I forgot to mention this because we are considering the point A. Okay, so this is not 0. Okay, this is our assumption that our capital Nm is not 0. Okay, so by the Coulomb law, we can get the formula for the n1, n2, n minus 1. So the ni is the determinant of this equation of the coefficient matrix. That is the Jacobian determinant of this. Okay, in the denominator we have the determinant of the coefficient matrix, which is the Jacobian determinant of x1 xn minus 1 to u1 un minus 1. But this is precisely nm. Using this equation, this determinant is precisely minus 1 n plus 1 multiplied by nm. So here we get minus 1 n plus 1 nn. Okay, and then the determinant of what? Determinant, you want to compute ni. Ni is replace the ith column of the matrix by the right hand side, the column vector at the right hand side. Therefore, we have x11, x1 I minus 1. Then the right hand side minus x1 n. Then we continue x1 I plus 1. Originally this is x1 I, but we must replace by Coulomb law. We must replace this by the right hand side. That is minus x1 n nm. Okay, and eventually this is x1 n minus 1, the last term. The other row are the same. x1 n minus 1, xi minus 1 n minus 1 minus that is this minus x n minus 1 n then x n minus 1 I plus 1 x n minus 1 n minus 1. So this is the expression for the coordinate ni, the ith coordinate of the vector n. Okay, now this determinant can be simplified because the nn can be cancelled. The nn here and the nn of this column, they can be cancelled. And then the minus 1 n plus 1, the minus sign can also be cancelled because we have a minus 1 n plus 1 at the denominator. They can be cancelled. Then we move this column. This is the ith column. We move to the last column. Move to the last column. Move here. You move a step. You change sign. The determinant change sign once. So from this consideration, we see that we can simplify the expression of ni to be minus 1 I plus 1, determinant of x1 1, x1 I minus 1, then x1 I plus 1. The ith column has been moved to the last column. Therefore, after I minus 1, you need to follow by I plus 1. Okay? Then x1 n minus 1. This is the original last column. But we need to add a column. That is the ith column for the previous matrix. So this is x1n. And similarly, the other rows are the same. Minus 1, xi minus 1 n minus 1, xi plus 1 n minus 1, x n minus 1 n minus 1, x n minus 1. So we obtained this matrix. What's the matrix?